Hydrogen bromide adds to alkenes to make alkyl bromides. This reaction occurs with great regioselectivity. We see strong preference for making the alkyl bromide that is more highly substituted. This regioselectivity is summarized in something called Markovnikov's rule, which states that the hydrogen adds to the alkene carbon having the greater number of hydrogens. This is the same thing as saying we make the more highly substituted bromide. In any case, this is an electrophilic addition reaction that takes place by the standard two-step mechanism. Now take a look at this. When this reaction is run in the presence of alkyl peroxides, we see the opposite regioselectivity, something that's called Anti-Markovnikov Addition. The bromine adds to the less substituted carbon. How can we rationalize both outcomes? Selectivity for the more highly substituted bromide or the less highly substituted bromide? Well, let's take a look at the mechanism for the standard addition of HBr to the alkene, and then contrast that to the reaction when we add alkyl peroxides to the reaction mixture. Following the standard first step for electrophilic addition, the pi electrons of the alkene double bond are used to make a sigma bond with the electrophile, in this case, a proton. This pair of electrons stays with bromine to make bromide as a byproduct. That will become important in a minute. You see I've drawn that proton adding specifically to the carbon that has more hydrogens. Alternatively, the proton could add to the carbon that has fewer hydrogens. But we don't see formation of this carbocation. To understand this, we need to look at the energy diagram that looks at the formation of both of these carbocations, the secondary carbocation on the bottom or the tertiary carbocation. Keep in mind we're talking about the reaction at the bottom. We have two alternatives. The hydrogen can add to make the more highly substituted carbocation, the one I've shown in light color on the left, or the less substituted carbocation, the one I've shown in bright blue on the right. Looking at the reaction diagram for this electrophilic addition, we see two humps. The first hump is greater. It's a transition state that leads to formation of the carbocation intermediate. It is this step that determines the reaction rate, and it is this step that determines the regioselectivity of the reaction. The proton adds to form either the tertiary carbocation or the secondary carbocation, which is less stable. Because the cation is less stable, the transition state leading to that secondary carbocation is less stable. This is something that's known as Hamlet's postulate, and makes sense here. Because the transition state is less stable, the activation energy leading to that secondary carbocation is greater. Of course, greater activation energy means slower reaction. So the smaller activation energy for formation of the tertiary carbocation intermediate dictates the regioselectivity. We can rule out the formation of the secondary carbocation because it's so much slower. In the second step of the reaction, a bromide nucleophile, remember, we formed bromide as a byproduct in the first step. We'll see that bromide add to the carbocation. This two-step reaction mechanism, which preferentially makes the tertiary carbocation, accounts for the high regioselectivity that we observe. So why do we get the other selectivity when we have peroxides present? Well, take a look. This combination of reagents actually generates a small amount of bromine radicals. This happens by this two-step process. First, a very weak oxygen-oxygen bond breaks to make alkoxy radicals. In fact, for every molecule of peroxide that breaks, we make two alkoxy radicals. When we track this with arrow pushing, we would write it like this. The fishhook arrows showing one electron going each way to make alkoxy radicals. In a second step, that alkoxy radical reacts with HBr. A single electron now from each reacting species makes a sigma bond. And this leaves one electron to stay with bromine. Here's the bromine radicals that we need for this reaction. Take a look at what happens next. The alkene pi bond reacts with a bromine radical. Again, a one electron reaction, which puts one electron on this carbon. The bromine attaches to the less substituted carbon to make the more substituted radical. The formation of the alternative radical doesn't happen. In this case, bromine doesn't add to the more highly substituted carbon. The explanation is exactly the same as we talked about for the carbocation intermediate. Once again, the light curve shows the energy diagram for formation of the tertiary radical, the one I've shown at the left on the bottom reaction. It's more highly substituted and more stable. The possible intermediate in bright blue is a secondary radical, and it's less stable because it has less alkyl groups stabilizing it. So just as we talked about for the carbocation, the transition state leading to the secondary radical is less stable. There's a greater activation energy for formation of the secondary radical, so it happens slower. Preferentially, we more rapidly make the tertiary radical, as I've shown below. This is the step that determines the regioselectivity, and the regioselectivity that we observe is exactly the same. In both cases, the more highly substituted radical or carbocation is formed preferentially because it's more stable. The only difference between these two reactions is what atom adds first. In the standard electrophilic addition, it's the proton that adds first. In radical HBr addition, it's the bromine that adds first. So we've cleared up the mystery about the regioselectivity, and it simply remains to add in the last step, a step where this intermediate radical reacts with HBr. The single electron from this radical reacts with one electron from this sigma bond. The other one stays with bromine. In addition to forming product, we regenerate a bromine radical. This makes bromine radicals a catalyst, really, doesn't it? HBr is consumed in this reaction, not bromine radicals. So now both these reactions make sense. In both cases, the regioselectivity is a result of forming a more stable intermediate first. And think about this from a synthetic perspective. We now know conditions where we can add HBr to an alkene to make an alkyl bromine with either regioselectivity. We can make the more highly substituted bromine or the less highly substituted bromine. As you can imagine, we'll find this to be very useful in organic synthesis.